Welcome again, and today we are starting with the fourth lecture by Wadey.
Okay, thank you very much. So I'll continue from where left on Wednesday. So I introduced the quiver-Yangian in the second lecture. So starting from Wednesday, I want to explain what is this quiver-Yangian BPS algebra. Right. So let me first summarize what we covered on Wednesday. So we want to first look at the special case when the quiver comes from toric-Claviel threefold. So we want to look at the type 2A string on a generic toric-Claviel threefold. And we want to look at this half BPS sector, which is given by the D-brane bound states with 1 D6 charge and no D4, and some number of D2, and some number of D0. Okay, so the word volume theory of this D-brane bound state, word volume theory, is aimed for quiver quantum mechanics. So the information of this toric-Claviel threefold is translated into the information of the quiver and the superpotential. And the information of the number of D2 and D0 charge is translated into the rank of the gauge group. So, and then, so for each arrows inside the quiver, we have a chiral bifundamental field. And so they give an dimensional representation of the quiver. And remember that we also have the so this chiral bifundamental field has to satisfy the we have to satisfy the F-term constraint and the D-term constraint. So the F-term constraint is just dW equal to 0, where the W is this superpotential here. So we see that last time that this F-term constraint gives you the path equivalence. So so this means that we're looking at, so this phi I give you an a-dimensional representation of the Jacobian algebra.
If it is bifundamental, will it be n a dimension, or one will be n?
Sorry, I didn't hear it. Sorry, I didn't hear it. Say again. Say again.
You were saying they are bifundamental, right? Phi I is bifundamental, or?
Yeah, right. I mean, so this is a. So here the A means all the A's.
Okay.
I mean, this is means this just this
the collection. Okay.
The collection. Yeah. So this transform is I mean it's an NA by NB matrix.
Thank you.
And so the Jacobian algebra is defined as the path algebra of the quiver divided by this the path equivalence that's given path equivalence given by the divided by the path equivalence that's defined by the F-term constraint. And and then we also have the D-term constraint, and so the D-term has this Fi parameter there. So different value of the Fn parameter. So the D-term constraint translate into the stability condition, and the different Fi parameter correspond to different chambers of in the moduli space of this representation. So for us, to start with, we will consider the non-commuted DT chamber. So this corresponds to the simplest framing, where we have so this is the framing vertex. There's just one arrow connecting to some a particular vertex in your quiver. So we call this A hat framed vertex. Okay, and then so because this is a toric clavier, so we have a U1 cube action. So among these three U1, there are two U1. They are global symmetry. And the other one give you the R symmetry. So in the end, we're considering the solutions of this phi that satisfy the F-term constraint and D-term constraint that also is invariant under U1 square. So when you put all this together, so there's a one-to-one map between the NA-dimensional representation of this Jacobian algebra to a NA codimensional ideal of this Jacobian algebra. And this ideal have to sit inside a Jacobian subalgebra where all the paths starting has to start from this frame vertex A. So you're writing all your all the paths have to. You can just start from at this framing vertex here. So you start from infinity and then the frame vertex and then to some any color A here. So what's so special about the toric quiver? So for the quiver and superpotential that come from toric clavier 3. So the superpotential has some special properties such that you can repackage this information of the quiver and superpotential into a periodic quiver. So this is the Q2 is the selection the collection of the phases. So this corresponds to the superpotential. So each phase inside the Q2 corresponds to a term inside the superpotential, and the orientation of this phase corresponds to the sign. So now this Jacobian subalgebra corresponds to a 3D colored crystal. That's from the uplift of this periodic quiver, starting from a vertex with the color of this framed vertex. So here a path inside this is starting from infinity to A hat to something to A. So this will correspond to a atom of color A inside this 3D color crystal. So this 3D color crystal is it's a full crystal that's starting from something at some point, but it has it's infinite along all the other positive directions. I mean, the positive direction are given by the arrows starting from this A hat. So I think last time I explained in detail the case of the C3 case. So for the C3 is have this quiver, and the superpotential is I1. And the periodic quiver is given by this lattice. So, so last time I tried to explain that for this case, all the paths that will correspond to. So if you uplift this periodic quiver, you get a cube of infinite size. That's starting from here, but then it's infinite along these 3 directions. And then each path here will correspond to some box inside this crystal. I think last time I stopped here. So today I want to explain this. First, explain how to visualize this finite codimensional ideal of this Jacobian algebra in this 3D crystal. So.
Are you looking for something to be raised to the board?
Yes, yes, yes. Any questions so far? I guess it's so. Let me just draw this full crystal for the C3 case. So you start from the origin, and then you have this cube that's the infinite size along these 3 directions. So this cube will correspond to. I mean, here there's only one color, so it doesn't matter this projection here. So this will correspond to the entire Jacobian algebra. So what is the ideal? So we want the ideal that's so the ideal is some subset inside this, such that any element inside the ideal and any element inside this I times a path is still inside this ideal. So you see there's a direction inside this crystal. So if you start from a some atom inside this crystal, and then if you multiply by a path, the positive direction is this 3 direction. So when you multiply by another path, it can only go deeper into your crystal. So then that means that the ideal of this Jacobian algebra is just anything that's removed, this full crystal removed by a finite tip from this origin. Is it clear?
No, can you repeat?
So maybe I draw it this. Does it have? So is it clear this picture? So we have this cube, and this cube is infinite along these three positive directions. Okay, and then so I want to find the ideal of this Jacobian algebra. So this Jacobian algebra, the element of Jacobian algebra is all these paths up to path equivalence. And then we said that each path equivalence, each path up to path equivalence corresponds to an atom. So in this case, it's just a box in this cube. So suppose you have a element. So the ideal means that some element inside this I, and any element inside the J such that I and J is still inside I. So so that means that suppose I start this atom that this is the thing that's inside I, and then so the paths always follow from these positive directions. So and then if you follow these directions, you're going only in these three.
Okay,
so
I can see that.
It's getting deeper and deeper inside your crystal. So that means that if you now I remove some piece from the tip. For example, I can remove one box and look at the complement of this one box. Then you're here, and then you can only go deeper. So any a full crystal with the tip of the crystal removed, that would be an ideal. Yeah, so that's a statement. So let me write it here. So so here there's only one color, so I didn't write this projection. But in general, so we want to look at the ideal of the. But this ideal has to be inside this Jacobian subalgebra. So this has to be the full crystal with the finite tip removed. So equivalently, we can also consider the complement of the ideal. I mean, this is an infinite dimension. So then we have, then the complement ideal is a finite dimension, which is just given by the tip that you just removed, meaning that this is some finite piece that you can grow starting from the origin. So this also is often called molten crystal in the crystal melting picture story. Okay, so for the case of C3, the ideal is this three-dimensional cube with some finite tip removed. And then this molten crystal is just correspond to the plane partitions. So you can check whether this picture is correct. So the plane, so we know that the generating function of the plane partition is this, the Mac-Mahon function. It's 1 plus Q plus. So so this 1 means that there's one vacuum, and then Q is so here that means that there's one. So this 1Q means that there's one possible configuration for the with one box. And here this 2 means that I want to consider all the possible configuration with 2 boxes. So there's 3 possibilities here. Okay. And then 6, I mean, you can just check that it's indeed, this give you the counting of the plane partitions with a number of boxes.
Do you have some intuition why this infinite product generates all plane partitions? Some, maybe, I don't know, maybe some construction of these partitions from this product? How do they generate it? Maybe this is just, we first do it by singles, then some doubles. Oh, but this is 1 minus q squared power 1, 2, and 3.
If I have the intuition about this, then I can write down the generating function for the partition, generating function for the solid partition, but that doesn't exist. So I'm not sure whether there's a.
Okay.
I mean, there's this famous story of the McMahon. So this is a McMahon function. So then he said, okay, I have the. So this is the generating function for the plane partition. For the ordinate partition, is just this. This is the generating function for the Young diagrams. I mean, this is the number of partitions for integer n. And then he said, okay, I can write down the generating function for any dimension. And then he wrote, and then he checked for up to, I think he checked up to q to the 6th, and then he wrote a paper, and then it actually turned out to be wrong at q to the 7th. So I think there's then, look, I mean, the definition of this generating function is that you count each configuration once. So I mean, this measure, you choose the simplest measure. So this is this is a plane partition. So now if I change from 3 to 4, so the 2 is this generating function, the Young diagram, and 3 is the plane partition, and 4 is called solid partition. Already from here, if you have this trivial measure, then I think the generating function doesn't have a closed form. So this is, I think, some Indian group. They just compute all this using brute force by computer, and then they take the precisic log of that, and then they see that there are minus signs there. That means that you can't interpret it as the multi-particling of some single particle partition, single particle generating function.
Yeah, so the McMahon function, I've seen that in the resolved Carnivore partition function. So when you take this product and then the infinite ray, that's when you add this factor in. That's yes. Right. So, right. For the other club, this also comes as a factor in front with the power of the Euler number. So this is some infinite tower of D0 rays.
Yes, exactly. So here for the C-thread, there's only D0. There's no 2 cycle. So it only have this plane partition. So yes, exactly. So this McMahon function exactly counts is the BPS partition function that counts the D0 bound state on the D6. And as Daniel said that for the general club, this will be a factor in front. Will be a factor of the arbitrary of the partition. So for general case. you also have this crystal picture, and then you can compute the crystal generating function, and this should come at the BPS partition function of the D2, D0 state bound to the D6. And then they normally have a factor of the Markov function that comes to D0.
You are taking D6 to be 1, right? Always? So
Sorry? I don't have D1. I have
D6.
Yes, I have one D6.
Yeah, it's always
yes.
1.
Yes. I need something, I still need to say something about this molten crystal. So you see that when we say we remove a tip from the full crystal, that means that I remove one atom and then I remove another one. So you can't remove something that's deeper inside crystal before you remove the atom that's on the surface. So you can't create, you can't dig a hole in there. I mean, you have to remove them. So, so that's the so-called melting rule. So this melting rule is quite easy to understand if you think of them. Think of this as just removing some finite piece starting from the crystal. So now, if I want to phrase this rule in terms of this finite piece, that I want to start from this finite, starting from the vacuum, I want to grow some finite piece, then I need the equivalent of this rule. It's called, we call this adding rule. Means that you have to have some rules when you add atom one by one, starting from the vacuum. So this rule is a bit tedious to explain, but this is actually a very important rule for later. So let me try to define this properly. So to state the adding rule, we need to define the precursor of an atom. Okay. So intuitively, the precursor of the atom A, so suppose you have an atom, so A here, of color A. Its precursor is just always nearest neighbor along the negative direction. So any, for example, for this guy here, it has two precursors. So it's any atom that's inside this Jacobian algebra, such that there's an arrow B from B to A inside GOQ1. We start from this atom B, and you multiply by this arrow, you reach this the atom you start from. So now, so the adding rule is that, so suppose I start from a crystal configuration. That's a complement of ideal. I want to add an atom here. So in order to add this to this K, I need to add this A to K such that this K plus A is also a valid crystal, means it's also another complement ideal. We need all the precursor to be already inside. So this is I mean, it's tedious to say, but you can just visualize by the complement of this rule, which is melting rule. So the last piece of ingredients we need before we start to describe the algebra is that, so remember on Tuesday afternoon, when I define this BPS algebra, I need in this algebra there's this parameter, the weight for each arrow. So here it just corresponds to the so this weight just corresponds to the complex mass of the scalar inside your inside the chiral bifundamental. So now with this, we can define the so this is the equivalent weight of the each arrow. So with this we can define the equivalent weight of each atom. So remember that each atom corresponds to a path up to the path equivalence. Then this the weight of the atom is just correspond to the sum of all the paths. All the arrows where these arrows inside this path, they correspond to this atom. And so because this path is up to a path equivalence, so that means that so if you so the consistency means that we need to impose some constraint on this all this weight. So that means that if we sum over all the weight along a loop, it has to vanish. This is called the loop constraint. So now we said that this for this toric case, so all the BPS states that we want to consider can be described by all this. So here, this is some valid crystal, the finite piece. And then now we want to build this BPS algebra, starting from this. So remember that the original BPS algebra, the fusion is roughly speaking, you want to combine the two states into another one. So this is hard to describe. So the idea is that we do not consider an arbitrary fusion process. Instead, we consider the fusion with one unit piece with an arbitrary one. So in this language, that means that we start with an arbitrary crystal, and then we add another unit piece. So here is just the atom. And then we reach another, the final state, we need it to be a valid BPS state here, which is described by the crystal. So that means that we want this BPS algebra to act on this the Hilbert space. So the Hilbert space is a representation of the BPS algebra that we want to construct. So this is just so this gives the raising operator. And we can also define the Cartan and the lowering operator. And we want to define the action of this algebra such that it can mimic this fusion process. So in particular, we want to, means that any state, after you apply this BPS algebra, you can reach any other states inside the Hilbert space. And then we want to want this action to obey this adding rule. And we want this to be implemented automatically. So we want to first fix the action, using this condition to fix the action of the algebra. And then from fix on any state. So because this is on any state, so from there we can find the relation of these generators on any states. So then the BPS algebra is just given by the free algebra generated by all these generators divided by this the relations. So in some sense, so this is how we find this algebra to start with. So in some sense, we're bootstrapping the algebra by its action on the BPS states, and then from there we generalize to more general quiver. Yeah, I think this is a natural place to stop.
Okay. Questions? Okay, so let's stop recording.